So welcome to Everyday Mathematics. Today we are on the MIT Integration Bee Semifinals 2026, and we'll be on the past problem of semifinals number 1, which is the limit as n tends to infinity of the integral from x equals to 0 to x tending to infinity of the square root of n times, open bracket, e to the power x minus 1 over x to the power x, close bracket, to the power n. So this is a very interesting problem, and it's a problem that uses a very interesting technique to solving such problems, the Laplace method of approximating integrals. And so before we even attempt to solve this problem, we are going forward to introduce this concept of the Laplace method of approximating integrals before we actually solve it. Okay, without much ado, let's move forward. So let's try to understand what Laplace method for approximating integrals is all about. So imagine we have an integral Im where m is a very large number, which equals to the integral from x equals to a to x equals to b of e to the power, and this is an exponential function, e to the power m, the large number, times the function of x. And let's try to express fx as a Taylor expansion around its maximum value x naught. So fx is equals to fx naught plus f prime x naught. This is the first derivative of fx times x minus x naught plus a half f double prime x naught times x minus x naught squared plus the remainder, which is the succeeding terms, where fx is maximum at x naught. Now we know that a function fx at the maximum point, its derivative is 0. So f prime x naught would be 0. And so our fx can be now approximated as fx naught plus now a half here times f double prime x naught times x minus x naught squared. But for a function that is locally maximum at x naught, it means that the second derivative is going to be a negative. So if we are to take the absolute value of x naught and then introduce the sign, these two expressions would be the same. Therefore, Im can be approximated as this first term is a constant, e to the power m fx naught times the integral from x equals to a to x equals to b of e to the power negative half m times the absolute value of f double prime x naught times x minus x naught squared. So let's try to express this integral part here as a Gaussian integral. First, let's express everything here as a square. So we have e to the power m fx naught times the integral from x equals to a to x equals to b of e to the power negative, open bracket, the square root of m times the absolute value of f double prime x naught over 2 times x minus x 0 or x naught, close bracket, squared. So this is good. So let's try now to express this as a Gaussian integral. So this is where we had our problem previously, right? So let's say let y be equal to everything within the bracket here. And so dy dx would be equal to this constant value with this going to 1. And so, in other words, when we multiply both sides by the reciprocal of this, we say now that the square root of 2 over capital M times the absolute value of f double prime x naught dy can be used to substitute for dx, which is a good thing. Then let's see when x equals to a, and since a is less than x naught, we're going to see how now we can take the a to infinity as we are moving the variables from the x domain to the y domain. So first, since x0 lies between a and b, then we can say that the integral here that we had becomes from the x domain to the y domain. So we're changing dx to dy. So this constant, we've pulled that out. And at a, since a minus x naught will be a negative value and m tends to be a large value that tending to infinity, this becomes negative infinity. And so b minus x naught is a positive value, and since m is a large value, that tends to infinity. And then we have e to the power negative y squared in place of whatever we have here. And so as we can see here, this is a Gaussian integral, which is a well-known integral. And that means that our integral becomes e to the power m fx naught times the square root of 2 over m times the second integral f naught absolute value times the square root of pi, which is what results from this Gaussian integral. Then we can just combine the square roots. So we have the answer being e to the power m fx naught times the square root of 2 pi over capital M times the absolute value of f double prime x naught. And this is an important answer that we are going to use now to solve our integration. So on to our problem. Limit as n tends to infinity. So n is a very large value of the integral from x equals 0 to infinity. Square root of n times open bracket e to the power x minus 1 over x to the power x, the power n. Now we can re-express x to the power x as e to the power natural logarithm of x to the power x. Now using the rules of logarithm, this power x, this x can come out, and so we can re-express it such that the integrand now, and even we can pull this constant out, so we're now focusing with just the function with the x's. Okay, and then now using the rules of exponents, we can now say this is the same as e to the power x minus 1 minus x times the natural logarithm of x. Okay, in some instances people would write log. Here we choose to use ln to represent natural logarithm. So this here in the numerator, in the power of e, is going to be our fx. Why? Because we can now re-express this in such a way that n here, the power, is the same as n times x minus 1 minus x natural logarithm of x. So since n here is a large number, remember we had an m that was large, so our fx would be x minus 1 minus x natural logarithm of x. So which is important. Okay, so let's focus on the integral for now. Okay, so we had that integral problem, and now our fx is x minus 1 minus x natural logarithm of x, where capital M equals to the small n here. Okay, now the first derivative of fx is 1 minus 0 minus natural logarithm of x minus 1, which is negative natural logarithm of x. And as you can see that for this to be maximum, for fx to be maximum, this negative natural logarithm of x must be equal to 0. Therefore, the x happens, the x naught for us now will be at 1. Natural logarithm of 1 would be 0. And the second derivative, f double prime x, is equals to negative 1 over x, which means that f double prime of 1 is equals to negative 1. So this is important for us. Now remember, since our integral where m was a large number came to this, And since we have our integral, forgetting the limit for now, where n is a large number, and fx is x minus 1 minus x natural logarithm of x, and x naught is 1, so fx naught 1 is going to be 1 minus 1 minus 1 natural logarithm of 1. The natural logarithm of 1 goes to 0, so we have 1 minus 1, which is going to be 0, and therefore we are going to pull e to the power n times 1, which is n to the power 0, which is 1. So the constant here is going to be 1, and so we're going to have limit as n tends to infinity of e to the power n 1 minus 1 natural logarithm of 1, and then we're going to still have the second derivative as negative 1 n times negative 1 over 2 x minus 1 squared. And then this is as simple as that, because this now collapses to 1. E to the power 0 is going to be 1. So we're just left with this integral here, where n is a very large value. So we may not need to waste a lot of time trying to convert it to a Gaussian integral. We're just going to use this formula here, where we saw that the f double prime of 1, or x naught of 1, where x naught, which is equals to 1, is going to be the negative 1 here. So we have the absolute value of negative 1, and then we have n in place of m, and then we have 2 pi. And then obviously this constant here is going to remain here, as shown here, which is important. And as you can see, the square root of n and the square root of n would cancel, and therefore we won't have any n remaining, and then the answer, since absolute value of negative 1 is positive 1, we're going to be left with the square root of 2 pi. Now, this is important, right? And that means that our answer is 2 pi. And that was the answer that was expected. So in order to solve this problem, you had to have knowledge of how to use Laplace method of approximating integrals to be able to solve this problem.